Today we shall discuss GSR analysis by instrumental methods. There are two types of methods which are used for the estimation of GSR particles. The examination is carried out either by chemical analysis or by instrumental analysis. Of the two methods, instrumental methods are far superior because of the simple reason that they are more sensitive, more accurate, and they are less time consuming. There are many instrumental methods, namely spectrography, atomic absorption, flameless spectrometry, neutron activation analysis, and X-ray fluorescence. Out of these, we shall discuss only those methods which are more suitable for forensic science, in the sense that these methods are non-destructive and their sample preparation is not required. In one of the cases, one of the types of analysis, the examination is carried out by X-ray fluorescence. This method requires very small amount of sample, is non-destructive in nature, and is at the same time requires no preparation of the sample as well. The X-rays are allowed to fall on the GSR particle and they get absorbed. The excited atom will emit its characteristic X-rays. These X-rays are so characteristic that they depend upon the composition of the sample, and these characteristic X-rays are identified by diffraction of the crystal using Bragg's law. The formula 2d sin theta is equal to n lambda, where n is 1 in this case, and lambda can be known after we measure the value of angle theta and also know the d of the crystal which deflects the X-rays. The diffraction of X-rays and measurement of theta will give the wavelength of these characteristic X-rays, identify the element present in the GSR. This method is non-destructive, more useful in forensic science. Apart from this method, the other method used is NAA, which stands for neutron activation analysis. This is an ideal method because it can detect particles present in parts per million, and this method is called referee method because of its sensitivity. It requires no preparation of the sample. The sample is bombarded by neutrons. These neutrons make some of the atoms radioactive. The radioactive atoms emit characteristic gamma rays which are specific to the particular element. They are identified by scintillation counters, both for qualitative and quantitative analysis, and the composition is very well known. These methods specifically suit forensic science because they are non-destructive in nature and they can be presented in the court as evidence.
After studying this module, you shall be able to know about neutron activation analysis method for analyzing GSR, about the importance of NAA in the field of forensic science, about X-ray fluorescence method for analyzing GSR. Introduction to neutron activation analysis. Neutron activation is a general term for irradiating material with neutrons to create radionuclide. Neutron activation analysis was discovered in 1936 when Hevesi and Levi discovered that samples containing certain rare earth elements became highly radioactive after exposure to a source of neutrons. From this observation, they quickly recognized the potential of employing nuclear reactions on samples followed by measurement of the induced radioactivity to facilitate both qualitative and quantitative identification of many elements. NAA is an extremely sensitive technique useful for performing both qualitative and quantitative multi-element analysis of major, minor, and trace elements in sample from almost every conceivable field of activity scientific of technical interest. For many elements and applications, NAA offers sensitivities that are superior to those attainable by other methods and are of the order of parts per billion ppb or better. NAA is generally recognized as a referee method of choice when new procedures are being developed or when other methods yield results that do not agree. Worldwide applications is so widespread that approximate by 1 lakh samples undergo analysis each year by NAA. Methodology of neutron activation analysis. The basic essentials required to carry out an analysis of a sample are a source of neutrons and their moderation, instrumentation suitable for detecting gamma rays, a detailed knowledge of the reactions that occur when neutrons interact with target nuclei. The sequence of events occurring during most common type of nuclear reactions used for NAA, namely the neutron capture reaction, is shown. It may be noted that prompt gamma rays are emitted and its study comes under the heading PGNAA and measurements are taken during irradiation. Delayed gamma ray neutron activation analysis DGNAA, where the measurements follow radioactive decay. Out of these two, the later operational method is more common. Thus, when one mentions NAA, it is generally assumed that measurement of the delayed gamma ray is intended. About 70% of elements have properties suitable for measurements by NAA. Procedure. Natural sodium, that is 23Na, is taken as the target. Capturing of one neutron will be convert it into 24Na radioactive sodium. The usual procedure involves placing the sample to be analyzed plus a number of suitable standards into the neutron field produced by a nuclear reactor. The sample is then analyzed using an appropriate gamma ray detector system. The 24Na decays to stable 24 mg with release of gamma rays having energies of 1368.53 and 2754.9 keV. On striking a suitable detector, the gamma ray energies are converted to an electrical signal that is processed as a count in an energy spectrum. The accumulation of gamma counts at a particular energy generates a curve, the area of which is proportional to the radioactivity of the characteristic radionuclide. Comparing against standards allow determination as well as abundance of a particular element. Most of the instruments used in forensic science make use of the changes that occur in energy levels of electrons of the atom under different conditions such as excitation, bombardment, vibrational stretching, bending, etc. As we know, chemical differences between elements are a function of the number of protons in the nucleus of their atoms. The nuclei of atoms of a given element always contain the same number of protons. However, the number of neutrons in an atom of the element may vary. We also know that the nucleus of an atom is a tightly packed structure, unlike the electrons, which can be easily dislodged or changed in various ways. Atoms of a single element containing different number of neutrons are called isotopes of that element. Every element has a number of isotopes and for the most part they are stable. However, when the neutron imbalance becomes too great, the nucleus becomes unstable and the element becomes radioactive. Radioactive elements decompose into smaller atoms to become stable. In the process of decomposition, they emit energy in the form of alpha particles, beta particles, electrons, and gamma rays. During decomposition, each element emits gamma rays at wavelengths uniquely characteristic of the element. Applications of NAA in forensic science. It has wide applications in agriculture, anthropology, biology, chemistry, geology, and medicine. Analysis of bullets, paints, glass, metals, gunshot residue, GSR particles. Documents may be examined for analysis of paper, clays, filling materials used in paper manufacture, soils, rare earths. X-ray fluorescence and wavelength dispersive analysis. Wavelength dispersive analysis. Many substances show fluorescence under ultraviolet rays. It means such substances have the power to receive radiant energy of a certain wavelength and to convert this energy into a higher wavelength within the visible spectrum consisting of different colors. Thus, fluorescence is a phenomena where a low wavelength of ultraviolet light invisible to eyes get converted into a higher wavelength in the visible spectrum and one can observe the same being visible to eyes. For example, an invisible small stain of semen when exposed to ultraviolet radiations from a UV lamp gives a whitish blue color glow. Similarly, we can carry examination for many other common articles of physical evidence, namely comparison of paper, currency notes, secret writing, sealing waxes, glass, threads, anthracene powder, and urine stains. The essential difference between UV fluorescence and X-ray fluorescence is that in UV fluorescence, the incident UV of lower wavelength exhibits fluorescence in the visible spectrum, which can be clearly seen. In case of X-ray fluorescence, the incidence X-ray as well as fluorescent radiation both are invisible to the human eyes, as both the radiation incident and fluorescence lie in the invisible spectrum. But the basis fact remains the same, meaning thereby that an incident X-ray radiation will be of lower wavelength and fluorescence radiation of higher wavelength. Principle of X-ray fluorescence. X-ray interacts with matter in many ways like absorption, scattering, and diffraction, etc. Absorption of X-ray is used for determining elemental composition of a sample, and the method is known as XRF or X-ray fluorescence. The sample to be analyzed for elemental composition is placed in the path of X-ray beam, which will get absorbed by the sample. The absorbing atoms get excited and emit X-ray of characteristic wavelength of elements present in the absorbing material, and this process is known as fluorescence. As the wavelength of the fluorescence is characteristic of excited atoms of particular elements, measure of this wavelength would enable one to identify the fluorescing element. The greater amount of elements will yield greater intensity and small amount will show less intensity for the sample. Reason being that intensity of fluorescence depends on how much of the element is present. For calculating wavelength, Bragg's law is applied, which can be derived as shown. For the ray diffracted by the second plane of crystal, the distance CBD represents the additional distance of travel in comparison with the ray reflected from the surface plane. Angles CAB and DAB are both equal. Therefore, CB is equal to BD is equal to AB sine theta is equal to D sine theta. CBD is equal to CB plus BD, which is equal to AB sine theta plus AB sine theta. X-ray fluorescence and wavelength dispersive analysis. D sine theta plus D sine theta is equal to 2D sine theta. To observe a beam in the direction of the diffracted ray, CBD 2D sine theta must be some multiple of the wavelength of X-ray, so that the diffracted waves are in phase. N lambda is equal to 2D sine theta, where n is the order of spectrum and for first order n is equal to 1. Lambda is equal to 2D sine theta. Quantitative analysis. According to Bragg's equation, lambda is equal to 2D sine theta, where D is the space between the crystal layers of the analyzing crystal and hence known. Therefore, known value of D and measuring theta can be calculated. The element is identified once the wavelength has been calculated and chart of fluorescence wavelength of all known elements consulted. Instrumentation. Source for producing X-ray. Suitable filtering of primary X-ray. Production of fluorescent radiation characteristic of element present when the sample is hit by the beam. Passing of fluorescent radiation through a collimator. Separation of different wavelength by the analyzing crystal. The intensity of each wavelength is determined and recorded using a synchronized detector which rotates in an arc around the analyzer to cover different angles for different elements present in the sample. Applications. Characterization of soils, trace elements in plants, detection of insecticides poison on leaves, fruits and vegetables, analyzing of ores and alloys, to distinguish between good quality and poor quality of rubber on the basis of presence of sulfur, analyzing of ceramics, determination of additives in motor oil, examination of antiques, examination of steel objects regarding chromium content, gunshot residues, GSR particles. Advantages. This is a non-destructive technique and thus the forensic exhibit remains unaltered. Sample preparation in general is not required. It is a very sensitive method of analysis. Detection limit can be 10 ppm, far superior to normal chemical methods. Amount of sample required in very small, which makes it more suitable for forensic work. Flameless absorption spectrometry. This absorption spectrometry is an extremely sensitive and convenient technique for evaluation of the GSR particles. It is so sensitive that it can detect elements in microgram and picogram ranges. It works on a simple principle that element absorbs radiation of the same wavelength as it emits when excited. The suspected element in GSR is taken in an atomizer, a graphite tube or tantalum strip, and is excited by heating. The radiations from a discharge tube with our suspected metal electrodes are passed through the atomizer. The loss of intensity in radiation gives the quantity of the metal in question. The technique is very useful and popular for the examination of GSR particles. Advantages: it is cost effective. Time taken for analysis is reasonably less. It can detect lead also. Disadvantages: one element can be detected at one time. Method is destructive in nature. Neutron activation analysis was discovered in 1936 when Hevesi and Levi found that samples containing certain rare earth elements became highly radioactive after exposure to a source of neutrons. NAA is an extremely sensitive technique useful for performing both qualitative and quantitative multi-element analysis of major, minor, and trace elements in a sample. Prompt gamma rays are emitted and its study comes under the heading PG-NAA and measurements are taken during irradiation. The nuclei of atoms of a given element always contain the same number of protons. However, the number of neutrons in an atom of the element may vary. X-ray interacts with matter in many ways like absorption, scattering, and diffraction, etc. Atomic absorption spectrometry works on a simple principle, that is, an element absorbs the radiation of same wavelength as it emits when excited.